4.3. Questions. How can I tell how many of each kind of subatomic particle are in an atom? Are most atoms the same? How is atomic mass determined? Terms. Isotope, mass number, isotope notation, unified atomic mass unit. Are all carbon atoms the same? 4.3 Useful notations. It didn't take long for Rutherford's nuclear model to supplant Thomson's plum pudding model as the prevailing atomic model of the day. But the amazing pace of discovery about the atomic world suggested that Rutherford's model soon would be modified too. You'll learn more about that in the next chapter. For now, we'll focus on the three basic subatomic particles and how chemists and physicists have developed notations to easily identify the numbers and arrangements of those particles within an atom. These symbols will help you understand the various properties of each element. Atomic number. We have already mentioned that the atomic number of an element is the number of protons in the nucleus. The atoms of each element contain a unique number of protons, which determines the identity of the element. If the atomic number of an atom changes, then its identity element also changes. It is very important to know the atomic number Z of an element. The size of an atom's positive nuclear charge determines the number of electrons surrounding the nucleus of an electrically balanced, neutral atom. In electrically balanced atoms, the number of electrons is equal to the number of protons. Mass number and isotopes. After Chadwick's discovery of neutrons, scientists could explain an observation that had puzzled them. When ionized atoms of a single gaseous element were shot between electrically charged plates, the electrostatic force deflected the atoms. But not all the atoms were deflected the same amount. There seemed to be heavier and lighter atoms of the same element. Since these atoms all had the same number of protons, the differences among them were linked to differences in the number of neutrons in their nuclei. Repeated experiments confirmed this observation. If the number of neutrons can vary from atom to atom in an element, then the atoms of a given element are not truly identical, contrary to what Dalton and other 19th century scientists thought. Physicists and chemists call atoms with the same number of protons but different numbers of neutrons isotopes. Isotopes of an element generally have the same chemical properties, but certain physical properties that depend on mass, such as density, evaporation, and diffusion rate, vary between isotopes. In order to identify the isotopes of a given element, scientists established the mass number A. The mass number is a whole number that is equal to the sum of the protons and neutrons in an atom. A equals Z plus N. Isotopes of an element are named by writing the element's name followed by a hyphen and the isotope's mass number. For example, the most common isotope of oxygen, Z equals 8, is oxygen-16. An atom of oxygen-16 contains 8 protons and 8 neutrons. The name of an isotope is sometimes shortened to just the element's symbol followed by a hyphen and the mass number. For example, oxygen-16 can be written O16 and carbon-14 can be written C14. When chemists want to indicate the specific isotope in a chemical expression, they use a special notation called isotope notation. This notation is based on the element's symbol and includes the mass number as a leading superscript and the atomic number as a leading subscript. The generalized isotope notation is shown at right. The isotope notations for oxygen-16 and carbon-14 are respectively written as 16, 80, and 14, 60. In some instances, the atomic numbers can be omitted from an isotope's notation since the element's identity implies the atomic number. If chemists are considering a group of isotopes of the same element, their notations are often written without any of the mass number superscripts. The reason is, in this case, the table of isotopes clearly lists each isotope as the same and is implied by the element's symbol. In some instances, the identity of a particular isotope can have real consequences for its physical properties. For example, hydrogen has 3 known isotopes, 1H, 2H, or D, called deuterium, and 3H, or T, called tritium. Notice that we have omitted the atomic numbers from the notations in this example as described previously. The most important deuterium compound contains 2 atoms of the 2H isotope and is written as D2O, called heavy water, which in large quantities is poisonous to humans. Its only large-scale use is in nuclear reactors. Tritium is radioactive and highly unstable. It is an extremely toxic radiation source, even in small quantities. Tritium is used as a trigger in nuclear fusion bombs, known more commonly as hydrogen bombs. So for hydrogen, having an extra neutron or two makes a big difference. Atomic mass. Once the chemists of Dalton's day started to analyze chemical compounds, they tried to determine the masses of individual atoms. They knew that water was made of hydrogen and oxygen, containing 8 grams of oxygen for every 1 gram of hydrogen. Because no one knew the real formula for water, Dalton assumed that there must be 1 atom of each. Thus, water's chemical formula would have been OH. So he assigned the smallest atom, hydrogen, a mass of 1 and oxygen, a mass of 8. We now know that the real formula is H2O, so oxygen's mass is really 16. Chemists express these masses in Daltons, or Unified Atomic Mass Units, DAY or U. You may see it abbreviated AMU, but this is viewed less favorably. An atomic mass unit is currently defined as 1/12 the mass of a carbon-12 atom, or as approximately 1.66054 times 10 to the negative 27th kilograms. It is about equal to the mass of a proton, 1.0073 atomic mass units, or a neutron, 1.0087 atomic mass units. The electron is far less massive, 0.00055 U. Why are atomic masses not whole numbers? In nature, samples of even pure elements are mixtures of the element's isotopes, which have different mass numbers. Thus, an atomic mass, as printed in references such as the periodic table, is the weighted average of the masses of the element's isotopes as they occur in nature. A weighted average is an average that gives more importance to certain values than to others. In the case of atomic mass, more common isotopes, higher percent abundance, are given more weight than less common isotopes. Thus, the listed atomic mass is closer to the mass of a typical atom than a simple average would be. For example, a sample of chlorine is made of 2 chlorine isotopes, Cl35, 34.969 atomic mass units, 75.76% abundance, and Cl37, 36.966 atomic mass units, 24.24% abundance, 24.24% abundance. The simple average mass of these isotopes is 35.968 atomic mass units. But because Cl35 is 3 times as common, it is much more likely that a randomly chosen atom would have the smaller mass. Thus, the weighted average atomic mass of a sample containing innumerable atoms will be closer to 35 atomic mass units than to 37 atomic mass units. Remember also that since your final answer is a sum, it can have no more decimal places than the least precise value being added. Though we know 3 decimal places in 8.961 U, we know only 2 decimal places in 26.49 U. Therefore, the sum of the 2 values can have only 2 decimal places.